Hi, today we're starting lecture number 29, where we get back into pavement design and talk about how we do pavements. You should have seen this last year when we did the sophomore class, the Intro to Transportation. We cover pavement design in that and how to work with pavement designs, calculate ESALs, and so forth, and a little bit in how to do layer analysis and calculate your structural numbers and finally find your depth of pavement. We're going to cover a lot of the same stuff again in the next, but shorter and faster than we did before. We're going to cover a lot of the same stuff again because now we're going to use it in our design projects, right? So this class, the whole point is hopefully you'll be geared up and ready to do roadway design or transportation facilities design. That's the title of the class. And part of that is knowing how to specify what pavement you've got. And so that's what we're going to talk about today. So we're not going to probably get as much into the weeds as we did last year, but we are going to recover or recap some of that and summarize it. And then we're going to see how we apply that into a design project through there. So that's the goal with this next couple lectures on pavements. Through there. And then in the first question we asked this last year, right? What's the function of pavement? Why do we have pavement? What's the whole purpose of it, right? What's going to affect our design? What environmental factors, what other factors are going to affect how we design pavement, and what our I guess solution finally is for a certain project through there. And finally, what's an ESAL and how do you find it? So hopefully you remember all of those from last year. If not, we'll cover it again, right? So why do we need pavements? We need pavements because the pressure on the tires of vehicles is great enough that unimproved soil can't usually support it. Right. In some places, yeah, sure, you can. There are really hard soils in places, and you don't actually probably need a road, or at least not all the time. Right, through there. Sometimes it's seasonal. All right, through that. But in general, especially in the U.S. and especially in northern Indiana, our soils are not strong enough that you can just drive on them with standard tires. And so the whole point is to spread the load out so that through the pavement, the load is being spread out through the pavement. So by the time that force radiates out of the tire through the pavement and contacts the soil underneath, it is below. That pressure is below what the soil can handle. And so then it's safe and it doesn't fall. And this is an example. You could add these treads on to a standard truck and you're getting a larger surface area. If you look down here, you get a slightly larger surface area, enough larger surface area that softer soils could support the load on this tanker truck, right? It's probably for an agricultural purpose. Right through there. The pressure in these tires is typically around 100 psi, 100 pounds per square inch. Right. The soil probably can't handle more than 50 psi. Right. So we've got to dissipate enough of that, or spread that load out enough so that we drop down below 50 psi, just in general. Right. So we're distributing load. Here's some different ways we do it. We had these paddles we added on to these trailer tires and the tandems in the back. You could have a lot of agricultural equipment just has really fat tires, and so this is probably a lime spreader or some form of spreader that goes out over the fields, right? And they got these huge tires, these big balloon tires on both the front and the back. It's to distribute the load. And if you look compared to like a standard dump truck, this is not a very big bed. It's not going to be hauling nearly as much weight as a full-size dump truck would, like over here. Right, and that's also reducing the load on the tires, which reduces the load that the soil has to bear, and you're better off with it. All right, and here in a dump truck situation, when these pull into a construction site, quite often it's kind of muddy and it's not improved, and there's no pavement there. They've got these tag axles they can drop down, or lift axles, and they can there's a switch inside the cab there that drops these, and so you can go from what your road configuration probably is, which is a front axle and tandems on the back. Then you add 2 more axles, and so you can distribute the load even more through that, right? And so that takes that pressure off of just those, what used to be, I guess, 12 locations where you were in contact with the soil through that. Here's what happens if you don't have a big enough tire and you hit soft soil, right? It just buries itself. Right back here it was okay, but you got off a little bit too far here, and then the truck will just bury itself through that. And in the pavement, this is what we're doing. This is actually from your sophomore textbook, that we've got a wheel load here, and it is just spreading that load out as it goes through the pavement. Right, here's our surface of the pavement down through the subbase, right? And that force radiates through there. It's a kind of a cone shape. And by the time it gets to the bottom of the surface layer, here's the subgrade, which is the dirt. By the time it gets to the bottom of the pavement layer, we need to have this distributed load being below what the soil can handle, and with some factor of safety too, all right, through that. So that's the game. That's what we're trying to do. And we've got both flexible pavements and we've got rigid pavements. Flexible pavements are hot mix asphalt. That's what HMA stands for. And this is going to be not all, but probably the majority, I don't know, 60, 70% of pavements, at least in Indiana, tend to be flexible pavement, HMA. Right through there. Yes, there's a fair bit of concrete pavements out there as well, but if you notice, a lot of the smaller roads, especially in towns and out in the counties, they're all asphalt. Interstates tend to be about half and half, right? Although I would say there's still probably a little bit more asphalt mileage than there is concrete mileage. And it's a calculation on cost is what it all comes down to. And INDOT on most of their projects requires designers to allow both options. And so a contractor can choose during the bid process on any project of a certain size and larger. They can choose in a bid project whether they're going to use concrete or they're going to use asphalt. And that's the idea, is to keep it competitive. So you actually have to do two designs. You have to do a concrete design, rigid pavement design, and you have to do a flexible pavement design in case they want to use asphalt. And our technical term for asphalt is HMA, hot mix asphalt. So this means that they heat the aggregate and the liquid asphalt oil basically up to a certain temperature, mix it together. That makes it hot mix asphalt, HMA, through there. So on your plans, at least in Indiana, you're going to see everything's listed as HMA, right? The other option is PCCP, which is Portland cement concrete pavement. So that's the other option, the other material, right? So it's either black or white. That's our two choices generally through there. And there's really, I mean, people try other stuff often on, nothing's really stuck, so to speak, through there. This is what our pavements sections will look like. We've got a surface mix, which is usually a tighter, smaller aggregate mix. And then we've got intermediate or base, and then we're finally down on the subgrade, right? And what we're showing here is that if you've got good subgrade, so this is the CBR is the California bearing ratio. If you've got a high CBR value, that means it's a pretty stiff soil that can handle a lot of load. Right, a 100 means you could drive on it with no pavement. All right, so at a 10, you're 10% of that. This might be a mixed design, and it depends on how many trucks actually, and how much traffic you've got driving over it, how deep this would be through there. But as that soil condition deteriorates and it can't handle as much, right, down in the 6 and 10 or down to the 3 and 6 over here, we're going to need more asphalt up above, more pavement depth, more constructed pavement to give us enough time to radiate that distributed load out far enough to drop below what this soil can handle. All right, and so CBR is a nice quick number you can look at, and you know how close you are or how good or how bad that soil is, right? So if you have a 10, you're in a pretty good soil, and you don't need as much pavement for it, all right, because it can handle a higher load right here at this interface through there. 3 to 6 is not very good, right? 15 so years ago, INDOT had a standard sections for all of their roads, and you would just look in the book for how many ESALs you've got, and you would pick out what the depths of your pavement should be. They get a little bit of a range, but there wasn't too much design involved. They just had all these standard templates in there, and it would show you what these layer thicknesses would have to be. And it was a one size fits all for the entire state. And, well, what about soil conditions? Well, they didn't really care. They assumed everything had a CBR of 4, I think, for the entire state, right? So pretty bad soils. We had really thick pavements back in those days through there. They've changed their design format since then. It's a lot more dynamic now, and we've ended up with sometimes, half the pavement depth we used to have through then the projects. And we did a project in early 2012, 2013. It is right about the time they switched that system, and we literally ended up with half the pavement we thought we were going to need based on the original NDOT specifications. And then, in the middle of design, which takes 4 years, they changed their standards, and then suddenly we didn't need near as much pavement as we thought we were going to have, which saved them a lot of money. So we had this big budget, $2 million or something, and we ended up, 300,000 or 400,000 of pavement didn't get spent out of that, and that went back in the state coffers through there. So that's the idea there. The stronger that pavement, the less depth of asphalt you need for that. And this is a flexible one. This is an actual design set of plans. This is showing what how we typically call out what our pavements are going to be. And so we've got the section K. That's this blacked in box here that says this is section K. And if you want to know what section K is, you can see there's different layers kind of drawn in there. If I can find my pen quick enough here. Oh, pen left. Pen left. All right. Come on. Where'd you go? All right. Here we go. So we've got these different layers here. All right. You can see those different layers are kind of drawn in there. All right. And then this box here is showing you that item K is this. And so this is each layer. Here's the top layer. Stop it. Here's the top layer, the second layer down, the third layer down, and then it sits on this fourth layer. Right? So let's see if we did this right. Here's our top layer, right? Here's our second, third, and fourth layer. So this is 165 pounds of HMA, hot mix asphalt. It's a type C mix. And so you check the state standards to find out what type C means. Through that, this is a low volume mix design. So they're using type C. High volume ones for major state highways and interstates. They have a whole different nomenclature, how they call those out. All right. This surface, so it's a surface mix. And with the, it's got a 9.5 millimeter. That's the size of the aggregate. That's about a 1/4 inch aggregate. So that's your top size on aggregate. And that is sitting on top of layer 2, which is 330 pounds per square yard of HMA, type C intermediate. That's the middle layer of asphalt. And a 19 millimeters is about a 3/4 inch top size in that. So we use bigger aggregate through there. And that all sits on 660 pounds per square yard of base, which is also still a hot mix asphalt, right? So it's still black. You'd call it asphalt if you saw it. Also has a top size of 3/4 inch on there. A lot of times on the base, we'll go up to 25 millimeters, all right? And so that's right around, what is that? Inch and a quarter through there. So a lot of times our base is actually 25 millimeters. This one we use a smaller aggregate size for that. And all of that sits on just aggregate, compacted aggregate number 53. That's NDOT's most famous standard base they put underneath their roads. And so this is I guess you would call it a well-graded mix, right? It has a range. If you remember from soils class, it has a range of sizes. I think it tops out at half or 1/4 inch, 3/4 inch, something like that, and drops down. Doesn't have very many fines. It does have some down to 200 sieve through there, but it doesn't have any of the clay, size particles and fines. So it's fairly well draining, but you can also, it works good as a base because with all that range of sizes in it, with that being well graded, it's got you can compact it pretty well. Right, and so it can become a pretty dense item, but also without the fines in it, it's also still drains well, so it makes it for a good pavement base. Because in the end, the constructability is an issue. You want to have a base that you can drive a whole bunch of dump trucks and the paving machine across as you're putting these other layers on, right? And so if you've got too fine of a sand or something, all that equipment is just going to rut it, and it's going to be a mess. And even though technically the sand maybe have a really good bearing properties and have a good modulus for bearing. They can handle a high PSI. It's the constructability may be really bad. We've had that problem before. Or if you've got like a clean number 8 stone or something, all single sized basically, or very close to it, those act kind of like marbles, and it's really hard to drive on, and you're going to put ruts into it. And then every time, every third or so dump truck that goes through, you have to come back through and try to smooth that out and roll it again, which is a mess. So the 53 is what NDOT specifies. That's underneath almost all their roads. If you end up being a consultant in Indiana, you're going to get sick of seeing number 53 base everywhere. But that's our normal material through that. Not a super high strength. It's not really even crushed stone. A lot of this time is aggregate, and it can almost be pit run right out of some of the quarries. They can just pull it right out of the ground, don't have to do much to it, and just put it in place. So it's not super high strength, but it does make a good base, and it's fairly well draining. So that's what way we use that. So that's our standard sections. This would have to show up on your plan sheets, right? If you're designing a road, you're going to have to pick these layers and these top sizes, and maybe what type of mix it is through that. And again, if you're working for NDOT, they've got a whole manual on just how to do that exactly, right through there. All right, and what you may or may, if you've had an internship so far as in the construction company, you may realize that 110 pounds per square yard is 1 inch of asphalt. And this is the theoretical or nominal maximum density that you can compact, or that's the goal density that your roller is supposed to be getting to, is 110 pounds per square yard for each inch of depth, right? And so NDOT likes to do it that way. I think it's because it makes estimating easier, right? If I know how many square yards of pavement I've got, I can just multiply that number of square yards times 165. I know how many pounds of pavement I've now got, right, in that surface layer, and then I can add in this and this, right? So if you divide 165 by 110, this would be 1.5 inch thick surface layer, right? That is the minimum depth you can use a surface mix for, right? And that the reason we have a quarter inch aggregate size is because that'll work really well with 1.25 inch depth, right? I think the max aggregate size you want to use, the maximum size of your aggregate has to be at not more than half your total depth of your layer. Could be wrong on that. I think you'd probably want it to be a little bit less than half your total layer thickness, right, through there. But this will compact nicely with only being 1/4 inch thick out of 1.5 inches. You can get a pretty dense mat. That's what you want on the surface, because you're using that surface layer to protect against rain infiltration. You want it to be a nice tight surface mix through there. Then this is a 3 inch deep intermediate, and then 6 inches of base. Why not just use all surface? All right, it's cost. This stuff costs a fair bit more than base, all right, through there. I don't know what the current values are, but standard numbers used to be, this might be like $70 a ton, and intermediate would be around $60 a ton, and base would be about $50 a ton, right? That's a general range. Numbers used to be. Now, I mean, this year the oil prices have fallen a ton, right? Gas is $1.60 a gallon right now. All those prices are going to drop, right? It is literally whatever the gas prices are, however the price of oil is per barrel. If you track that directly relates what price you're going to be getting from contractors for asphalt and placement through that, right? Type C was based on how much traffic you've got and how many ESALs you've got there. There's our top aggregate size, right? And if you might remember this curve, right, before, this is how pavement deteriorates. And so you've got a serviceability index over here, and this is the age of the pavement through there. You start out, everything's great. We usually say this is like a 5 or a 4.5 here, and then it drops. And it doesn't drop linearly. That's the speed that the pavement starts falling apart picks up as time goes on. And so that's keep that in mind, right? It's not a linear thing. And because it's not linear, the cost of repairing at this point, when it's gotten to this point down here, and you wanted to jump it back up like they did here, right? that cost of repairing it once it's gotten down far is much more than if you were to do a little bit of a treatment up here and jump this curve back up and then start that curve down again. Do a little bit of a surface treatment here. Maybe it's a chip seal, maybe it's a surface seal of some kind, right? So this is actually a lot cheaper going this much improvement than it would be to wait until the pavement got a bunch of potholes and started having other deteriorations. Whoa, I cannot draw straight that far and come up and then down. All right, I'm still not very good with this pen. All right, do that. So that's, just keep that in mind. It's better to do routine, regular maintenance, cheaper regular maintenance every few years than it is to wait 10 years to do a major repair, right? Just a general strategy through that. If you're going to design pavement, what do you have to keep in mind? You got to know trucks, right? What about cars? Right? We don't care about cars. Cars do nothing to pavement unless that's all that's driving on it. Then you would care about it. But if you've got more than 1% trucks on a road, all you care about is trucks generally for there. And that's any state highway, any major, even collectors, arterials, interstates, all of that. The only thing you care about is trucks. The cars do almost no damage to the pavement. It's all the truck traffic. And we're going to see here in a second. If you remember from last year, you'll remember that truth. Through there, we care about how strong the soil is, right? That'll directly affect how much pavement we need. All right, through there, we want to know how reliable do we think this road has to be. So at interstate, we pick a really high reliability rate for it. A small county road, if it fails, it's not the end of the world. It's not that critical. There's not a lot of people driving on it. It's so we don't need as high reliability. That'll save us some money, and we can use a thinner pavement section in the end, right? And then what's our definition of failure? How bad do you want the pavement to get before you call it done, right? Again, on an interstate or an arterial road, we pick usually a 2.5 would be our serviceability rating for that out of 5. If it goes below that, we'd say it's failed. It's not a good road and you can't maintain speed, and it damages vehicles and sometimes can be a hazard as well. On a small road, on a local street or a county road, we'd often say our terminal serviceability number is 2 instead of 2.5. We can allow it to get worse. People expect more potholes on those side roads and those small roads, right? So traffic, that's something you're going to calculate that. Soil strength, you get that from the geotech soils report. You learned all about soils last semester, so you know how to do that and calculate that soil strength now, right? Desired reliability, it depends on what kind of road you've got, and you're just going to look up the numbers for what kind of functional class you have, right? So arterials, you're going to say, well, we like to have 95% reliability on that, right? So, and so forth. And then finally, what's your definition of failure? Again, it's based off that functional class and maybe your jurisdiction, what they want to use for that. All right. This is the equation for flexible pavement. Hopefully you remember it from before, right? Doesn't everybody remember this from that? Right. It's crazy. Right. This is a huge monster and whatnot. It's held up over the test of time, right? They defined this back in the 60s at the ASHA road tests over in Ottawa, Illinois on I-80. In that area, they built those test tracks and tested all that and then came up with this, right? Through there, log of W18, this is the standard log, not the natural log. This is the standard log of the number of 18 equivalent kip axles that have passed that road. So that's your ESAL number, right? All right, sorry about that. You can also solve this number using a nomograph, which is a fun way to do it. You don't see that very often anymore, but it's still a fun way to do it. Coming back in here, SN is your structural number. That's directly going to apply to how deep your pavement is, right? And if you looked at this big, long equation, you see you got a structural number here, you got a structural number here, and here's your change in your serviceability index and so forth, and all that. Well, if you're solving for a structural number based on how much traffic or ESALs you think you're going to have, right? It's in 2 different places, and it's raised to certain powers as you're in there. Basically the the only way to solve this is by iteration, is to run through and iterate until you arrive at what your structural number should be, right, through there. And you can calculate, if I told you what the structural number to aim for was, you could calculate how many ESALs it could handle, right? That would work fine through there. But if you know your ESALs and you're trying to solve for a structural number, then you typically have to iterate to find that answer, which is Excel is excellent at. It works very well for it. Here's what the other terms were. I'm not going to spend a lot of time on that because it's not that important in this class, right? This is just to remind you the stuff that went into it in the last time. From last year, right? Structural number is really the number we want to come up with when we finally get there. Here's our soil resilient modulus, M sub R, that's the strength of the soil for that through there. This is the big one. This is your ESAL. This is your W18, is that a number of equivalent single axle loads that come through, right, through that. And in an ESAL, if you remember right, the equivalent single axle load, the ESAL is defined as an 18,000 pound axle loading. All right, through there. And then we've got charts that come through that. So this is if you picked up a tractor with a trailer, a short trailer, I guess, on this one, and dipped its tires in ink and then set it on a piece of paper. This is the diagram that would come out, right? This is where the tires are touching on that. That's where all of the load, whatever that truck weighs, all of its load has to end up in all of these dark areas, right, where those tires are touching the pavement. That's all that. It was an 80,000 pound truck. If you added up all the weight in each of those dark areas, these shaded areas, it's going to equal 80,000 pounds, right, through that. You may remember these. We did this again last year. You've got these charts, right? You have to, so here's the iteration piece, right? To calculate what an ESAL, how many ESALs your truck is, you have to assume a structural number for the pavement to start with. All right, so if I assume my structural number is 3, I can come here. How many pounds are on that axle? If it's 12,000 pounds, structural number of 3 with a single axle, right? And a terminal serviceability up here, 2.5. If all of those things are true, then I've got a 0.229 ESALs, all right, for that 12,000 pound axle load. So this axle load it's only 12,000 pounds, 18, right, is 1. Look at that. Oh, there it is. All right, so an 18,000 pound single axle is 1.0. All right, that's the definition of the whole thing, right? Through there. But if you have less or if you have more than 18,000 pounds, these are the factors that you've got, right? And you can look at how, as weight increases, how much the ESALs increase, right? So what's twice 18, right? 36, right? So if you double the weight on the axle from the standard ESAL, right, at a structural number of 3, you're going to get 17.7 times as much damage. You're going to get 17.7 times 17.7 ESALs from that single axle, versus if you'd only would have had 1 ESAL loading on that pavement, or if it had only been 18,000 pounds, right? And ESAL is kind of an indicator of damage, right? That's the number of equivalent single axles, right? So doubling up the weight on that axle is doing almost 18 times as much damage as what the 18,000 pounds, the standard axle, would have done, right? So it was the weight, the damage caused by weight is definitely not linear, and it's kind of, if I remember right, it's to about the 4th power, all right? And so if you double the weight of a vehicle, it will do 2 to the 4th power as much damage as it would have otherwise, right? So that's why cars don't count. Essentially, only trucks do, right? So if you went through and measured a truck and looked at the different axle configurations and how much weight was on each one, you can pop through here. All right, so here's our 12,000 pound axle structural. We're assuming a structural number of 3 and a TSI of 2.5. If your TSI isn't 2.5, you have to use a different table. All right, and if your structural number is 4, you got to jump over here and use that. All right, so we're assuming a structural number, and in the end, we may be wrong, and then we'd have to start over and we have to iterate again, right? That's part of the iteration piece on that. So that's that first axle, single axle is 0.229. Here's a tandem axle, 2.5 and the 3, 34,000 pounds, that's 1.1. And if we do a triple axle, TSI 2.5, structural number 3, all right, we're going to be down here. There's our 0.308. Okay, so that's the ESAL value for each set of axles. You add those all together, and then you get the total ESAL value for the entire truck. So in this case, because he's got a triple axle, actually helps him out a lot. Adding that extra tire, look, it dropped you from 1.11 to 0.308, right? Adding that extra axle, because it's not just a single tire. We only see one on this side. But adding that extra axle really drops that, right? And typically a truck is going to do about 4,000 times, 5,000 times, depends on your car, more damage than a car does, right? And so obviously one truck is equivalent to, even kind of a conservative estimate, 4,000 cars. That's why we don't care about cars. All right, just think about the ADT. If you've got 10% trucks, it's the trucks is really all the damage. You could add up all those other cars. It may add 1% more ESALs over the life of the pavement. It's all truck damage. So don't forget that as we go through here. We don't care about cars when we're designing pavement. Right, we don't usually know the exact weights and axles of trucks, and so part of our job as a designer, so this is straight up what you're going to be doing if you become a consultant and are working on these projects, is trying to figure out what pavement section I need. That's pavement and earthwork are the two most costly things on a construction project, right? And so getting your pavement set up right and figuring out what your depths are going to be as early in the process and your design project as possible is good, because then your estimates are going to be much more accurate as you go through. All right. So, if you were to make a mistake on that, on the ESALs, you may be showing 10% more asphalt than you need. Your client may freak out like, oh, this is going to be more expensive than I thought. I don't have enough money. We have to stop, so forth. Right. And that does happen through there. Or they may think, hey, we got plenty of money. We could actually do some extra stuff if you underestimate the ESALs and you have too shallow of a pavement, right? So don't mess that up, right? This is really expensive stuff and high dollar value. And it all starts with calculating your ESALs, right, as you come in there. There's my word to the wise. So we don't care about cars. We only care about trucks, right? And we don't, we just did this example where we looked at an exact truck and we calculated the ESALs on that vehicle. We can do that, but how often do you know exactly every configuration and every weight on every set of axles of all the trucks that go through your project, right? That's never going to happen, I don't think, ever, anywhere you're at. Oops, didn't mean to click there. And so what we do is we use an average estimate. And so the NDOT in probably every state tracks what the average ESAL values are of trucks on their roads. And they do it usually by class. And so there's, I think, 15 FHWA classes of vehicles. Usually the states don't use all 15 of those classes. So a passenger car is one, a pickup truck's another classification, a pickup truck with a trailer is another classification, pickup truck with dualies and a trailer is another classification, and so forth. And then you get up into straight trucks, and then you get into straight trucks with single rear axles, straight trucks with double rear axles, and then finally into semis, and then longer and heavier and more axles, and so forth. So there's a lot of classification. Buses is another class right through there. But in general, commercial vehicles, they can aggregate that and say the average, if you know what your truck percentage is, we can tell you what your average ESAL is for all of the trucks in that group of categories. It's usually more in the single FHWA category. But in the truck category, we can give you an average ESAL value for those expected trucks. And that's what we normally work with, right? And the way NDOT does this is they've got these weigh and motion stations out on mostly interstates, but also some major state highways, I think, as well. And typically truck routes. That's where they like to put these, right? Because that's where they care more about how much trucks weigh is on those roads. Through that, and they monitor those all year round through there, and they calibrate them off and on as they need to through that. But from that data, they can tell you pretty exactly what the average ESAL value of a single truck is and what a normal truck is on Indiana's roads. And so this was from a report from JTRP, the Joint Transportation Research Program down at Purdue, which works for the state Department of Transportation quite often on most of their research pieces. They were evaluating these weigh and motion stations. And so you can see here all these green diamonds are where they have a weigh and motion station. And I'll show you a picture of what those look like in a second, but you can get by the term way in motion means these trucks don't stop, they're just driving right across them. Now the state still has their standard truck weight areas, scales, and where they have trucks pull off and get weighed, but they've moved more and more to these way in motion ones, and then I think they quite often don't require all trucks to exit now when there's a scale on the interstates. They pick out the trucks and they have a light that indicates which truck they should do. They can pick out trucks that if they're just downstream of a way in motion area, they'll see which ones look like they're close to the limit and they'll have them pull into the scale. So it saves them a lot of time through that. The other thing though is it gives us all this really good data over an entire year and years and years as it goes on, right? And so there's a class 9 truck is this. This is our semi. That's our class 9. And so here's the number of axles passing in statewide at all these locations with the green diamonds for a week through there. And you can see here's how many axles are being generated by trucks, and this is in millions over here. Here's all the non-semi axles loadings, right? So there's a lot of truck axles, passing through there. If you think that, standard, well, it's only about 10% trucks. We're more than 10%, way more than axles. But of course, trucks have a lot of axles, so maybe that's part of it too. So this is the data they're collecting, which is a lot, right? And this is what it looks like. This is a weigh in motion sensor, and it's just set flush right into the pavement. All right, so you can see here's one, and then here's another one. They stagger them so they get one set of wheels on one set of wheels on the other. They prefer that than nowadays instead of going across the entire lane, because it's better for the rideability of the vehicle, right? Instead of both tires hitting something at once and getting a bounce, which you don't want when you're trying to weigh them. You don't want them to bounce much because it adds a dynamic force to it. Through that, and I think it may be also related to maintenance through there. They also put an inductive loop back here, just in advance of it. The inductive loop can measure. That's what they use for counts. They can count the number of vehicles who are crossing it. Also, the inductive loop does a good job on classification. There's usually a set of 2. There's one you can barely see off there. So they'll set these loops in there as well. And those loops are pretty good at doing the classification. So if they're moving this direction, the loop says there's a vehicle here. I know what class it is. These 2 sensors then, which are just load cells basically in the pavement, record what the weights of the axles are as they pass through that. All right, so that's the weigh in motion sensors. Here's another one, an older form of it, which were bigger. Through that, you can see this is a load plate through there. I found this I was just searching for pictures of it. Here's the loops right in front of it, right? I was searching for pictures of weigh in motion ones, and I found this pops up, from Google on Reddit. And so, are these hidden barricades? What are they for? So conspiracy theories. I think these are like little barricades that are going to shoot up out of the ground and block the road off. If I don't know, World War III or something happens, or the zombie apocalypse or something. So no, these are the weigh in motion sensors, right? And they are bigger than the other ones, but they are still per wheel track, right? So they split 2 per lane through that. So this is a slightly older style, but that's what weigh in motion does for you. All right. So how are we going to calculate our pavement? All right. So here's a little picture. This is US 30, and it's 4-lane highway, right? This is a standard, setup. The way in traffic, the way we refer to lanes, we got lane A is on the inside, lane B is on the outside. And so this is the A and the B lane. For eastbound, here's the westbound A and the westbound B lane. A is on the inside, B is on the outside, right? So which lane has more trucks, right? It's almost always the outside lane, right? Unless you've got a restriction and you can't have heavy vehicles on that lane. And it ranges. It ranges how, if you think about you drive down the interstates and whatnot, how often are trucks in the right lane? If there's 3 lanes, sometimes the middle lane has actually got higher truck volume than the right lane, especially in a congested area like 294 and the tri-state going around Chicago. There's a fair number of trucks in the right lane, but more of them prefer the second lane in through there. I think that's mostly a 4-lane in each direction, so that would probably be lane C. That tends to be where I see most of the trucks there. That would actually be your design lane through that. Where you've got 2 lanes here, so here we set this up as an example. Let's say our ADT out here is 40,000 vehicles a day. Remember, ADT counts in both directions, so it's counting both the westbound and the eastbound traffic. We've got 10% trucks. It's a pretty common number around here. The trucks using lane B in the driving lane, they use that 70% of the time. So only 30% of the time are they riding out over here in the passing lane, right, through that. And that becomes important later. INDOT tells us, based on their weigh and motion sensors, that the average ESALs per vehicle for a truck is 2.5. And we were designing a pavement for 20 years, right? So how many ESALs are we going to design for that 20-year pavement on a road with this traffic number and 10% trucks, right, through that. So we're going to work through this, right? So we got a 4-lane highway, ADT 40,000. How many we're trying to design the pavement, right? So we're trying to get down to pavement, and we're not designing pavement across all 4 lanes. We're designing pavement in a single lane. So we're going to start splitting this down. So we've got 40,000 vehicles per day. Only 20,000 are going westbound. Okay, great. We've got, of that 20,000, 10% are trucks, right? So in going in one direction, we've only got 10%. So that's 2,000 vehicles. 2,000 trucks a day are going westbound, right, in that single direction. Great. And now let's split it by lanes. And so in lane A, there's 30% of the trucks. So there's 600 trucks a day. And in lane B, there's 1,400 trucks a day. Right. So now we're down to trucks per day, and we don't care about cars because cars don't matter to pavement. Right. So what number are we designing for? Right? Are we designing for the 2,000? Are we designing for 20,000? This is often a point of confusion I found before. Right. So what we're coming down to, we want to design for this truck coming here in his lane. Right, now we're going to build both lanes the same, and that's a constructability issue. Is we can't change pavement depths halfway through the road. Well, maybe you can, but that creates a ton of problems. So we never do. All right, so whatever depth we're using in the right lane, we use in the left lane, but we only care about trucks in the design lane, and the design lane is the lane that has the most trucks in it. And so in this case, it's B. B is our design lane, and we are actually just for this pavement design, all we're designing is this pavement in this little orange box here, all right? Because that's in our design lane. And so we've broken it down. We're going to use this 1,400 because that's the number of trucks passing over this little box of pavement in a single day. And now we're going to scale that up and calculate the ESALs. But we're starting with, this is our traffic number. So this is what we care about, 1,400 trucks per day in the design lane. We're designing for 1,400 trucks per day. Keep that in mind. All right, so 1,400 trucks per day, 2.5 ESALs per truck. It gives us 3,500 ESALs per day in the design lane. 3,500 ESALs, 365 days in a year, or if you want to be super exact, 0.25 on there. All right, so we've got about 1.3 million ESALs per year driving in this lane. All right, through there. That's our design lane, as we said. So about 1.3 ESALs, a million ESALs through that per year. All right. If we didn't account for traffic growth, if we're happy with that number and it looks like traffic is super stable and we are assured it's going to stay stable for the next 20 years, we leave it alone. We just multiply it by 20 and you get 25 million ESALs. Sounds like a lot, right? 25 million equivalent axles are going to pass over this little spot over the next 20 years. That's what our estimate is, and that's what we designed for. And this is mid-range. This is mid-range for pavement. 25 million ESALs, that's mid-range, right? And we typically round these off, right? We're civil engineers. Our numbers are never that exact. Maybe we are through structures, but for highway, nothing we do is that exact. So we're going to round this off. In 25.5, 25 million and 550,000, yeah, that's good enough. All right, through there. Now, if traffic grows over time, we have to add a growth factor, and this is the growth factor equation for that. So we have 1 plus I to the n power minus 1 over I. I is the annual increase in percent as a decimal percent in traffic, and n is the number of periods, or in this case years, that it's going to grow at, right, through there. What's our normal growth factor range? It's usually 1 to 3%. And so we often use 1.5% as our common assumption for our growth factor for traffic. And trucks will grow at the same rate as all traffic, we assume. They usually do, right? So we plug this in. And so you plug that in, our growth factor is 23.1. And so if in that first year, our base condition is this, 1.3 million ESALs in the first year, multiplied over this growth factor, which covers all of the traffic that passes that point and grows each year over the next 20 years, we end up with about 28.4 million. You can round up to, typically we'd round up to probably the nearest 500,000 is pretty common. So 28.5 million ESALs. All right, so a little bit bigger than what we had before. It was our one before, 25.5. Now we're at 28.5. All right, so we designed for that. Still, we're in the mid-range of what typical pavement would be. All right, and something to think about, that's the total number of ESALs we think, based on that equation, that great big equation, that pavement can handle over its entire life. All right, if traffic grows at 2%, that pavement will wear out, will reach its terminal serviceability before 20 years is up. If traffic doesn't grow at all, and we still design for 28.5 million, great. We get 22, 23 years out of that pavement before it reaches terminal serviceability. All right. So this ESAL number that we were calculating is how many ESALs that pavement is designed to handle over its entire life. All right, I think that throws people off, and I think, well, we're just designing that ESAL number we're designing that's per year or something. Nope, it's like money in the bank. And every time a truck drives over that pavement, it subtracts $2.5 out of your bank account. You start at 28.5 million. Every time a truck goes by, it withdraws $2.50 or however many ESALs that truck is. And cars are withdrawing, half a cent every time they drive over it. It is something crazy like that. And so when that bank account is empty, your payment's done. You're just toast, right? You're putting a new payment in. And hopefully you're doing some preventive maintenance over time, and you can extend the life of it and so forth. But so that's our intro to traffic and how we're going to use it in design. And this big important piece, the first big important piece, is how many ESALs do you have? And so this is it, right? This is how we get there and find it. So you hopefully understand how an ESAL is calculated. You're almost never going to have to do it per vehicle and calculate the axles themselves and all that and use those tables. You're almost always going to use some average value someone gave you. Now, maybe they'll tell you, here's what our normal truck is, and then you calculate it once, and then you use it for every single truck that goes through there. But more commonly, you're going to probably be working for public agencies. They're going to use that, whatever state you're working in, what their average truck ESAL value is. And this is how you end up with. And so now we know what to design for. Now we know what to plug in. This is that W18 number in the great big equation. All right, this goes into there. All right, next time we'll pick up from here and talk about some more pavement.